Hey physics, this is the last video of the notes portion of projectiles and circular motion. In fact, this one is about circular motion, but I just thought of something else that I wanted to show you that could be so valuable for your videos when you're making your sports commentator videos. Um, when you think about like a projectile being thrown like a javelin, they are running down the lane and then they are throwing it. Each body part is also in motion too. And at the end, the speed of the javelin as it is being released is many different velocities add together. And I found this one picture on the internet of Boris Henry throwing in Sydney for the Olympics. And if you really look at how he has his arm completely extended, remember he is running. Okay, now he is running still at the same speed, hopefully, and now he is bringing his hand closer. Okay, he's also moving his whole shoulder before he moves his hand completely up there. So now he's running his shoulder, the addition of his shoulder plus also his body running. Okay, now his hand is whipping up there, his elbow is whipping up. Each motion, now the elbow is even further ahead than the hand, and then now the hand is at least going now. So each part of his body that is moving, plus the speed of his body too, all adds up to that speed of that javelin as it's just being initially launched out of his hand. Now remember, at 45 degrees and at the fastest speed is what you'll get your maximum range out of. And look at that. That's pretty much 45 degrees when you look at it. But that's real quickly what I wanted to talk about there. Here we're going to move on to centripetal forces driving on curves. Here's a picture from Active Physics talking about a car hanging on the curve. And we're thinking about it, here we've got this sign, and it's not saying slow down, it's saying, hey, warning, there's curves, because most of us who have some experience driving, we realize that curves and high speeds do not work. And why is that? And so there's a couple things that we do in class. One thing that we've done in the past, and we don't have a car that handles this really well. We've tied a motorized car in the string, and we've put it down in one spot, and our motorized cars, they jerk and they don't turn well. So this has never ever worked out well for us. But the whole idea is that if you get one of our little cars to go in a circle and then you let it go, that it's going to go straight at one point. This right here is circular motion, and there's something that has to hold it on. And so with our cars, it's going to be friction that's holding you on. Okay, but if you're going too fast, it won't matter. Okay, so let's look at this one. I brought up this picture because you don't hear about centrifugal forces very often. When I was a lab tech, we used a centrifuge all the time, and we would spin down these tubes of blood, and all the heavy particles would go to the bottom of it, and then we'd have the blood serum on the top. And so I know that centrifuges are the whole idea that like if you go and you spin a bucket full of water and you spin it around and around and around, that the water stays inside the bucket. We know that it's pressing down. And this is called a centrifugal force, but not a lot of physics teachers like to hear that term. And because they say it's all about the centripetal force. It's making no claims on this. Some people actually talk about it quite a bit, but it's making no claims on it. It's saying that we're just talking about a force that's a centripetal force, and that this force is what holds the car into the circle. Okay, it may be, in this case, it may be a string that is attached, but if that string is let go, it will go straight out. And this force is always going towards the center of it, the radius of it, but it is a force that keeps on curving it in, because otherwise it would go straight out perpendicular from the radius. Okay, so centripetal force is that force that is holding it towards the center of the radius, whether it is the friction on the tires, whether it is a string holding this car, whatever it is. So the centripetal force is the force that holds it towards the center of the radius and keeps it going in circular motion. Okay, if it was ever let go, this force was, then the car would just go in a tangent line, tangent to the circle for those of you who have taken upper level math, and which is perpendicular to this inner force here. Now, centripetal acceleration, that's talking about anytime it's going around in a circle. Now, the neat thing about this is, remember a long time ago we talked about acceleration? Something is accelerating whether it speeds up, slows down, and one other case. It could be going the same speed around a curve. It could be going the same speed around here, but if it changes direction, then that is called acceleration. That's the answers to one of your checking up questions, by the way. Anyway, it accelerates whether it speeds up, slows down, or if it's turning. Then it is accelerating. So centripetal acceleration is accelerating no matter what the speed is or if it's constant or not going around here. Okay, let's think about that car that we were just talking about. I just gave you a huge hint for this. Okay, if you had a car on a string in the path and it would follow and the string broke, right at the point where that car is located on this diagram, which letter would it hit? Now that you know everything in ninth grade, so many kids would have said F, E, C, B. They would have said all kinds of different things. But now that you know that it goes tangent to it, you know that the closest path would probably be D, because it's got to be perpendicular. It's going to just let go and it's going to go off perpendicular. Oh, goodness. Okay, and so now let's talk about the calculations, and these are written also in your notes too. Calculate the centripetal acceleration and the centripetal force. What are those variables? Okay, we know a lot of these ones. We know that acceleration is A. We know that speed is, or velocity is v, and in this formula, both of them, you've got to square the velocity, so that just tells you how important your speed is going around a curve mathematically. Okay, the tighter the radius, the more it's going to be accelerating. So the smaller the radius, the bigger your whole fraction will equal, so the acceleration is more, and the shorter the radius, the larger your force will be too. So it just goes to show, the sharper the curve, the more you have to slow down, because that speed really matters on your acceleration going around the curve. Okay, what are the units for all of these? Oh wait, let me figure out the stuff for the force one too. Let me get that here for you. Okay, the force is force, and F is force, M is mass. It has to be in kilograms, can't be grams, you'd have to convert it. Speed is in meters per second, and you'd have to convert that too, and radius has to be in meters. All the units are listed down here below. Okay, acceleration is meters per second squared. You've known that one. It has to be in those. Velocity is meters per second. Okay, the radius must be in meters, and F will be always in newtons. And we haven't talked too much about that. We will be touching on that in our next unit after we take this test. But that force is measured in newtons. Okay, so let's try a sample problem. Okay, calculate the centripetal acceleration and the centripetal force of a 1,000-kilogram automobile traveling 27 meters per second that turns on an unbanked curve having a radius of 100 meters. All of ours, and these ones, will be unbanked. Okay, banked means that the curve is raised at a certain angle. Okay, so let's start first with the centripetal acceleration. Okay, we will go and insert in for velocity the speed. Okay. And we've got to square that, and then the radius is pretty nice. It's already in meters, so we didn't even have to do any conversions, and that is going to be, don't forget you got to square that top number. It's going to be 7.29 meters per second squared, so that's what its acceleration will be at. Okay, looking at the force example, okay, we have to set it up with force equals mass times the velocity squared, or the speed squared, all over the radius, and I set it up there for you. Okay, we've got 1,000-kilogram mass, and we've got the speed as being 27 meters per second, and we've got to square that value. Oh goodness. And what we get out of that is we get 7,290 newtons out of it. Okay, that's all there is to solving those ones. So it's pretty nice, and you don't have to use one or the other to solve the other one. So it's pretty nice, and we'll be practicing some of these problems tomorrow in class. I do have some checkup questions for you to answer on there. Some of these are pretty nice. You've been given all the answers, so if you need to rewind this at all, that's great. Now the answers are provided for you in what I discussed. Oh, what is the force that keeps the Earth moving in a circle around the sun? I'll give that one to you since you were watching the notes and hopefully not copying. What do you think it is? It's gravity and centripetal force.